research-oriented drive. An ex-research fellow at Microsoft, she is now on the same tangent at Carnegie Mellon University as a research assistant in Advanced Agent Robotics Technologies Lab. She is the recipient of the ACMW Scholarship for attendance at research conferences and the prestigious City Women Leader Award. She is also part of the GE Foundation Scholar Leader Program. Ms. Vidhi Jain is currently working in an intersection of vision, NLP, and robotics for navigation by reinforcement learning and planning. It is an honor to have you here with us today, ma'am. Now, I request Ms. Vidhi Jain to take over the stage.
Thank you, Aditya. And it's really an honor to speak to my alma mater. I think one of the research inspiration did come from the CSA Art Talks itself. And I think during my first year, it was the time when someone from Microsoft Research, a prior BITS alumni, Nakul Gupta, was giving this talk. So really, I think this is a great opportunity for me. I'm Vidhi, 2014A7TS0113P, and I think that tag has stuck with me for life, like for not just those 4 years, but for life. And today I will talk about these things with you, about my BITSian life. How did I get into research? My research focus as of now, and I'll discuss some of my research projects and then talk about what's next. So starting with my BITSian life, I started BITS. I chose BITS because I wanted to do computer science and chose course over college. So something that I have always been proud of is being a nerd, and this photo is accidentally taken in a workshop, but I think it was fitting to get things started. This was first year, as many of you could know. But BITS did bring out a transformation in me. So yeah, here I am with my wingies and doing all sorts of crazy stuff. And yeah, I think apart from that, BITS gave me a community and gave me opportunity to engage in some volunteering work. So in my first year, I started at National Service Scheme for the Computer Literacy Program. And this is these are the images from the Nirman Association working towards Gift of Joy, where we interacted with underprivileged kids in Pilani and trying to introduce them to the concepts of computer science and different engineering aspects. So that was fun. Then I got more involved into technical development. Right from my first year, I was involved in ACM, then gradually rose to become a project coordinator. ACM also closely works with Apogee, our technical fest, and that gave me opportunity to work with several seniors on projects which greatly shaped my research interest later then. So something that I was finding missing was that there were about 40 members in our student association back then, and only 3 girls were remaining till the end of the first year. And as most things we learn is in the company of our peers, I thought that technical community was essential for me to grow. And to bridge that gap, we tried out an initiative in our 3rd year to bring up something called ACMW, which would bridge the gap between this skew gender ratio. Apart from that, I also got interested in Professor Rahul Banerjee's multimedia lab, and later I went into software-defined networking lab as well. So this is a point that I just want to relay some advice from my seniors, that you must believe in yourself and make the most of what you have. And this does require some exploration and self-motivation to start in something new, but that's kind of part of the process. And one needs to be persistent to look out for opportunities and understand what is the opportunity cost, as we say in economics. So I think one of the things that I I got to understand here was how we evolve through 4 stages of competence. So mostly when we are starting in something new, it is our unconscious incompetence. We just trying to learn about things which we may not understand or do not know how they are, and then gradually we start realizing, okay, we don't know this, and that's where the conscious incompetence comes in. And I associate this aspect as the imposter syndrome, when you realize that you're not um, confident enough about what you can do. But and sometimes it is the point where people start leaving out, dropping out, quitting what they're trying to do. If you stick there and continue to work hard, you can move to a next stage, which is called conscious competence, and you can take pride in what you do. And gradually, as you master your skill, continue working into it, then you basically come to that 4th stage of unconscious competence. So I think it's very important to realize this process, because for me in research, I'm always up for something new, trying out something new. And I'll discuss how here I evolved through this process. So in my first year, I told you I was involved in ACM, Apogee, and the multimedia lab. And then I also started out with some NGO, volunteering work with an NGO called Arise Impact. And there, most of the stuff that I did was mobile application development, which was cool back then, when I was just starting out. And I also tried to explore a lot about computer science in general. So my second year, I was thinking about what I want to do next, and then I went for an internship at FZI in Germany, where I got introduced like mostly to semantic web technology. Of course, this requires some background work, looking up what are the opportunities available. But yeah, you get to learn the meat of the subject when you reach your internship period, and try to work closely with your advisor. And similarly, that process of understanding your own capabilities continued in my third year, when I went for my tax internship. And there I think for the first time started closely looking into machine learning. It was mostly statistical machine learning, like in Bayesian networks, but that gave me some exposure to think about the larger scope of problems here. So coming back to the aspect of believing in yourself, um, there are some things that we all need to understand. So we often wait for brilliant idea to hit us like a lightning, and well, these ideas are actually quite abundant, and most of them won't know like would work or not until you test them. So the key idea is, like, these ideas are very cheap, and working on them will make them valuable. Okay, and once you start working on them, um, it's it's gonna be really hard, and you have to push it through. And sometimes you work on an idea and you realize, okay, it's already published. Um, what next? It feels like a dead end. But like, the best lesson out of that is that you are actually on a right track. And most researchers, while growing as in their young stages, don't realize it. So it is something important to realize that everyone has to go through this process of working on something and just finding that, okay, it already exists. It's just a clear indication that you're on the right track, or you're thinking in the right process like other successful people are thinking. And just when you are stuck in those dead ends, you just need to open your mind and look out for more ways in which an idea can succeed. And with that, I think I moved into the second phase of my career, where I'm currently a research master student at CMU RI, working with Professor Saikara to investigate algorithms for human robot teaming. And before this, I was a research fellow at Microsoft Research India, where I investigated unsupervised learning and divergence measures in GANs. I had looked into this deep generative models in general, but during my undergrad thesis at Mila, Montreal. And this is how I think my focus got shaped into machine learning and more towards the research. I do understand that we need to assess some opportunity cost when we are trying out some new projects. And these are the three things that I think which are very important. So something like utility is thinking about, will this project be useful if I could perfectly complete it? And what will be the metrics that would use to evaluate the success of this project? So thinking about what is the general utility of the product that I'm building. And then I think comes the feasibility aspect. So maybe in um, theory of computation, we study about, okay, P versus NP. Can something will be computationally computed or not? Is it feasible or not? A lot of times things can be done through approximation, and it's just very interesting to see a lot of things which people back then in the good old days of AI believed, okay, it's not possible. Deep learning and machine learning, they are just statistical techniques trying to approximate something, are able to find certain solutions. So I think thinking about the feasibility of your project also goes, it plays a very important role. And finally, understanding the risks involved in your research. What is going to be the broader impact of your work? And can you work on something which can make you unique or distinguishable in the same amount of time that you have? So it's a risk about spending your time in something which is not worth it versus something which can really pay off. So some practical tips to get into research: you should do the background work. It's called literature review, but it generally means that just want to get to know what are the existing solutions for the problem that you want to attack. And the way to go about it, which works for me, is understanding the pros and cons of an approach and the assumptions that they have made, and then sitting down and prioritizing what are the ideas I'm going to work on. I think second and third points just work in tandem. So you want to focus on something, build some tangible working prototype, and then step back and think about it more broadly, and think about what are the general assumptions that you could make here so that you can formulate a theory of it, make it more open for use in the other design cases which are possible. So both of these, I think you do a lot of back and forth between your focused mind and diffuse mind to be able to arrive at something which is useful. And I think for people who want to just get started, there's some reproducibility challenges at NeurIPS, iClear, ICML, and other top conferences where you can use your experience from studying the background work and trying out them to be able to showcase it at these conferences. And if you have a novel idea, if you want to submit a full paper, maybe you should try something such as student research competitions or workshops at different conferences, just as a stepping stone to get started. Finally, I think a lot of us have this question that what is the opportunity cost of research? So something, again, talking about the pros and cons, we can list what are the pros of working in a grad school versus industry. So this is a biased opinion of me, and everyone can have their own opinion. This is definitely biased by my experience, that I find that grad school, you can work closely with your advisors and a small group of students, whereas industry, you can often land up working in a big team. For grad school, you would plan your projects, ideas based on novelty, for different conference and journal deadlines, whereas at a job and industry, you want to work on the existing projects and their maintenance, and the focus is on the utility and the usability of that product. And again, the budget constraints are much, the budget is much scarce in academia versus industry. And I think this is a bias point, then grad school offers more freedom, in my opinion, than industry. So that's what got me into research. And now I think I'll talk more about what I am currently working on. So this is a topic that I'm very excited about recently, that how we can develop explainable AI agents that can understand and maybe collaborate with humans. And this focus is spread into three of these areas, which is, can we make these assistants personalized? So something which is very closely related to this personalization aspect is, can these AI agents understand the other agents in the environment and have a theory of mind about them? What it means to have a theory of mind is, can we think what these other agents are thinking about me? And this is something which humans do so naturally, but if you think about it, it's a very complex process that we are able to do. Babies, infants are not able to do it right away. It takes maybe a 5-year-old. Still, I think a 5-year-old still struggles with this concept of theory of mind, and it's pretty amazing that we humans actually develop this ability. So developing something such as an assistant for us would require incorporating these concepts into the AI modules to a certain extent. Second, I think it's about the explainability. And by explainability, I mean, can we explain the decision-making process going on in these AI assistants? People are trying to look into how we can explain a statistical machine learning model, which is purely learning rules based on data. Can we explain why those rules were learned the way they were? And I think finally the most important thing is their sample efficiency, which is very important to actually realize any of these agents in real world, because sample efficiency is something which is very clearly keeping all these machine learning and reinforcement learning experiments in simulation, and we hardly see them coming as a usable product to the community. So I think it's a good research topic, that how we can make these deep reinforcement learning agents more sample efficient. Okay, now I think I'll go more into one of the project that I did recently, and I'll describe this as so this is an initial step towards machine social intelligence, in our opinion, and we investigated particularly how to predict human strategies when they go about solving a search and rescue task in a simulated environment. And the motivation here is that we want to understand what is inside a human's mind, so that as an observer agent, as a robot who is observing this happening, they can proactively assist them with the critical information, which can help later to allow them to perform their task efficiently. So I think I'll just go a bit into the task formulation. So on the right, you see the map where different, this is the layout of the map where humans are given the task to find victims. And this is prior to disaster. So human rescuers' objective is to navigate this environment and rescue victims. Victims would have varying degrees of injury, so human rescuers have to think about what is the appropriate strategy so that they can save the most victims, and then critical victims are having more importance than the less critical ones. And the disaster might have caused some structural perturbations, such as blockages that may limit the ability of these rescuers to reach certain areas. So what our AI's objective is to identify how these human rescue strategies are going to be in this mission. And we have considered two of these strategies. First is victim saving strategy, whether they are saving critical victims first or whether they are just going and saving everyone they see next. And second is, how can we predict what is the next location they are going to visit? So based on their previous navigation trajectory, can we say anything about which areas, which rooms will they next visit? This thing, we tested this out in a Minecraft 3D simulation environment. And Minecraft is just, so for those who are not familiar with Minecraft, it's just 3D blocks placed in the environment. So our victims here also were denoted with just blocks of different types. As you can see, the yellow block was chosen to denote critical victims. The green block was for the less critical ones. The red refers to the one which has expired recently, and the critical victims expire after some time when the player enters the mission. And then a white victim is when a victim turns white when the player goes and saves it. So I'm just going to discuss about the contribution that was that I worked on largely. So that was towards next location prediction, and in that we processed the sequence of areas that the rescuers were visiting in different episodes. And the idea was that with some training data of how these rescuers visit different area segments, can we learn a model to predict the same. So again, the output was a probability distribution over all the possible next areas that the rescuer is likely to visit. And the architecture that we used here was a transformer model. And I won't go into the details of how a transformer model works, but for those of you who are curious, a transformer model is something which is very popular for language modeling. The natural language processing community, I think, came up with these models in 2017. And this is something which is going to be probably useful for any sort of sequential modeling task. How we train this is we use supervised training loss, because the signal about how you gonna train it, the labels, are coming from this trajectory in future. And this was our accuracy, that the sequence model, the neural sequence model that we were trying to use here showed human level accuracy. And apart from that, we also developed an evidence accumulation approach, which was to accumulate all the available domain knowledge explicitly, and then use this as an upper bound to talk about what is the expected performance of any neural sequence model, which is trying to learn this implicitly from data. And then we also compared this with what humans are capable of doing. So human observers' performance that you see here says what is their performance on this task, and we can see like humans are at par, probably lower than what we can learn from the data itself. So yeah, here the key contributions of our work. We evaluated predictive models on human rescue strategy and compared their performance with that of the human observers. Humans use their own prior biases, whereas neural networks need a lot of data. So for that lot of data, we actually did not go out and collect more trajectories from human participants. We actually developed some full human trajectories using planning and biasing those planning to mimic certain personalities of humans, and then use that to train these neural networks. And then the evaluation that you saw on the previous slide was only done with real human data. So yeah, and the third point I've talked about previously, that the evidence accumulation approach is a way to maybe see what is the upper bound that we could achieve with the data. With just having all the knowledge about the task, humans are still pretty random, and that's the upper bound that we could come up with, given that all the knowledge we had. So these were more like prediction models. And next I want to talk about what about explaining why these predictions were made. And I'll let you know why it is important, because when we are when our robot assistant or AI assistant is trying to make any suggestion to us based on its prediction, we would likely question it back, like, why would you say so? And it is important to think about what is a good way to understand the concept, the inner workings of this model. So one of the approach that I took here was a model agnostic one. So SHAP is a game theoretic approach inspired from Shapley values, where it's used to talk about how should I assign payoffs for in a team of where the players were acting collaboratively and their payoff was much higher. They got a big reward, but their individual contributions do not add up to that reward. So how do I differentiate? Like, how do I explain how much I contributed to the player one or the player two? So this technique has been studied in game theory, and they use something as counterfactual. Like, what if I remove this player one? What would be the payoff? And what if I added this player one later? What would be the payoff? So you average out those computations and try to come up with an explanation of the attribution to each person. And here I was trying to look into the same concept with some approximation, because clearly this seems very expensive to compute. And here it's the simple idea that a neural network model or a decision tree model or any sort of machine learning model, a black box, takes in some input features, and then it's trying to say some output, but what aspect of different features contribute to that output, to what extent, that is something that we can understand with SHAP. And I looked into this for the same similar task about victim saving strategy prediction and something like the knowledge condition, the prior knowledge the human participant had. And we can analyze something like such as mean feature importance for different models through this, that a classifier for victim saving strategy prediction, what features does it focus the most on for a sample of data set that was given. And similarly, we could do that for any other classifier. And these two models are just to contrast the way feature attributions look similar in and the actual features that were fed into these models were quite different. We could also analyze the prediction at a particular time step. So something like what happened when the features had these particular values. Can we explain why the prediction of this 0.98 confidence was made? So in this case, the model was saying that the player will go and save a less critical victim first. And the reason why the model was predicting so was because it had seen that when the mission timer was close to this 5-minute mark, and that's when the players know that the critical victims are gonna die around that time, so they start focusing their attention towards the green victim or the less critical ones. And something which is negatively contributing to this prediction is that player had not saved any green victim or less critical victim before, and that's kind of saying, okay, player will not save that again, and maybe it's gonna save a critical yellow victim. And similarly, another counterintuitive explanation here, where these features are kind of contrasting in the way that the model is saying that the player will go and save a critical victim, the yellow victim. And why it is saying so? Because it sees that the mission timer is so, and there is a beep beep signal saying that a very critical victim is nearby, and there's no less critical victim, green victim nearby. So that's why that's contributing to say that, okay, a critical victim will be triaged next. But it's very interesting to see that there are some features which are saying, no, maybe the critical victim would not be triaged next because the player has been saving less important victims like green victims, and there is no critical yellow victim in the field of view. So it's very interesting to analyze these machine learning models this way, because now you know what was in that input that contributed for and against the prediction that was given to you. And this has implications with different applications of machine learning models in loan disbursement, in employment and hiring, and much more important critical situations where we would like to predict. It's also a useful tool to analyze how these predictions actually is the machine learning model actually focusing on something which we as humans consider important or not. So something such as mission timer is very strongly correlated in data, but humans probably won't use it that often as much as this model is using. So it's very interesting to analyze the explainability here in machine learning models. And then I think I'm moving towards applying the same concept but to deep reinforcement learning. So what is deep reinforcement learning? It is that the player learns to, in this case, a card pole learns to take actions based on what it sees in its state space. So your model is a policy which looks at, okay, what's the card position, card's velocity, pole angle and pole angular velocity, and then it decides whether I should apply force to push the card to the left or to the right. And this is something which we typically talk about in reinforcement learning settings. So again, a same black box could come in here, which maps, which is a function that takes in the states and spits out some actions. And we want to analyze when this learned policy would say push the card to the left, why would it say so? So it's also useful to see what are some features in your state that heavily influence such decisions to be made. So something like here, pole's angular velocity is heavily influencing the decision to push the card to the left. Whereas the card velocity, which is already, I think, moving to the left, is saying maybe it should not be pushed to the left. And similarly, we could analyze it for more settings with more state features and more possible actions. And on the bottom, you can see this is being analyzed for one particular example. Like if you took the action to fire the right engine in this lunar lander, what would be the reasons why that action was taken and what are the features in the state which are opposing that action. So lunar lander is a simple toy problem where that lander needs to land on the surface of the moon, and you need to figure out how to balance the torques and land it in an upright position with both legs on the ground, so that that's how you get the reward in this environment. And you're just given the information about where your speed and angle and coordinates are. That was interesting because that was state representation which was pretty small, and it did not depend on the past observations. Something like PacMan, where your model takes in all the pixel values of the screen that you see on your PacMan and tries to predict out an action. That's something much harder to solve. So here, the PacMan is the small yellow dot in the center, and clearly the model's policy is trying to figure out which action to take by focusing the attention to the red aspects. Like the red aspects will contribute to take that action, and that's on the PacMan and a ghost up on the top here. And the blue things in the first action refer to what are the food bits available that you should probably neglect while taking this action. And this brings us to maybe these image-based explanations are not enough, and you want something like a verbal explanation. So that brings an interesting research question that can we have some verbal explanations for the behavior of these policies that we learn with reinforcement learning? And could SHAP feature importance be useful for these verbal explanation generation? And something, a second point which is very closely related is simulatability of these explanations. So it refers to how these explanations would be understood by a human who is trying to replicate this performance again of this original teacher policy. So there's a concept of student-teacher where you can imagine that the teacher tells the student to do something, but if you provide some explanation to the student, maybe the student learns better. So the same idea is reflected in these neural network or machine learning models, that if we are providing explanations along with the input-output pairs, is another network, a student network, able to learn it better than the teacher or generalize in some sense? So that's something about a research question. And now I will move into a related area of navigation policy and talk about how we can learn spatial semantic priors for navigation in an unseen house environment. So let me start with an example. Say you have to find some keys, and where would you look for it first? Now, we as humans often start searching by scanning the area closely and finding objects where you are likely to find the keys. For example, the tabletop in this case. On getting closer, if we do not find that object, we would navigate to maybe the next highest likelihood object where we could find that keychain. And in this case, we start moving towards the coffee table, I guess. So finally, I think we find the keychain near the laptop on the coffee table. And in all such scenarios, the proximity of that co-located object has influenced the path taken. So humans naturally use this common sense to build what kind of path you will take. And this is the key aspect that we were trying to look in this work, that how can we learn and contrast these semantic spatial representations. And we worked on having these embeddings that capture the spatial semantic prior. Can we use them for a simple heuristic-based navigation, which has a high success rate? Okay, so this starts with first step, training some embeddings, in which each object is represented as a vector in the embedding space with high cosine similarity to objects that are often co-located. And the second step comes when we want to use these embeddings for navigation, for searching an object in this house. Clearly, we do not have a map of this, but what we are trying to do is do an intelligent search here. So for a given query object, such as a credit card, we detect what are large enough objects in the field of view which are not already visited. They could be bed, lamp, table, and then we look up their embeddings and see which has a maximum similarity with our query keyword, like which is a credit card. And then we start moving towards that in adapted step sizes and repeat this until we find the query object. Here's the pseudocode for the previous example. Note that any embedding representations can be used as long as it has some function, some meaning of similarity between two object representations in that space. And the proposed plan that we compute can be computed by any planning algorithm. In this case, we used A* search. Okay, so these were some results, and our approach using some graph embeddings had resulted in high success rate and a high SPL metric. What SPL stands for is an inverse path length weighted metric, where you want to say what is the ratio between the optimal path length and the path covered by my agent in search of that object. And you take an average over all the successful outcomes that happen. And especially in large environments like kitchen and living room, we saw that difference was noticeable when there was a lot of distance between the agent start position and the eventual query object position. So the optimal path length was very large. And this was the key takeaway, that object-based priors can guide search and navigation in robots with a good improved performance of an intelligent exploration for that object. And this is noticeable when your optimal path length is larger between that agent's start position and the actual object. Because in a lot of cases, this is, so I think I can stress that point more by saying in a lot of cases, when the path length is very small, you see very inconclusive results that which of these embeddings were good, because it can so happen that you can find it often by fluke. Like you just move around and see around, you find it by fluke. So that drives these metrics inconclusive to a certain extent. And the future directions for these could be, can we have some way of adapting these embeddings in a few steps, in a few limited set of experiences, or searching in that same house? And can we investigate some sort of generalization and transfer learning for unseen objects? And so far, I have covered 2 of my recent projects on predicting human strategies and learning interpretable object finding policy for navigation. And here are some upcoming research areas where, again, connected to the theme of developing learning-driven assistants, which can be personalized, which are explainable, and which are sample efficient. And these are some closing remarks. I think it's very important to emphasize for people who are interested in research that all of you around are, we think that the other people are very smart, they can do something, but the reality is that they are no smarter than you. And once you determine that you want to change something, you can basically go after it, put in your effort, and you will see results. You will take some lessons and insight, but it will eventually accumulate, and you will see results. With that, thank you, and I'm happy to take any questions.
Thank you, ma'am. I'm sure this talk was an eye-opener for many students. We've got a few questions in the questions tab. If you could pick them up and answer it quickly.
Okay, sure. So where?
It's on the right side, the questions.
Okay, there's some question saying most research done in AI ML is termed useless according to many professionals. In order to get recognized, one tries to write papers and explore the popular and overexploited topics with less room to growth. What should one research about and with whom? And that's a very important question. Like, it's a good question to think about what are the projects and problems worth solving. And I think I tried to bring some stress on that by saying that understand the utility of the project that you're working on. Is it gonna be useful in broad scheme of things? And then decide what are some feasible ways to basically approach it or tackle it. At times it is coming up with a working prototype for something which is a simplistic version with some strong assumptions, and that's okay, because that's just a stepping stone for you to grow. And yeah, I think that's, maybe that answers the question. Okay, there's another question which is asking, the OpenAI's GPT-3 release, is it possibly close to human level intelligence? I do not think so, because GPT-3 is able to handle a lot of natural language generated sentences because it has just learned on a huge corpus of statistical text data. And then what it is lacking, it's possibly lacking these natural conversation, instruction-based conversation that you would want to give to a robot who's your assistant in a household. And think about a new word or a concept that comes up in some lingo or meme. Will GPT-3 have access to it with such small number of samples? So there are questions about, can these models, which are so huge and consuming a lot of data, can they do some sort of systematic generalization? And I think that's a very active area of research right now. But can you learn about a concept and then generalize to other kind of concepts? Okay, how to proceed after hitting dead ends repeatedly after doing literature review for a project. I think this is something which demotivates a lot of aspiring researchers, that you are bound to hit dead ends and you have to accept it. The literature review that you have done, think more carefully about the kind of dead ends that you're hitting. It can be that you're at times building a small working prototype, and that's taking a lot of, maybe implementation issues are coming up. So that could be a dead end. If some people perceive that as a dead end, in that case, go to your seniors, go to people whom you think have a knowledge about this, and try to get it solved. Try all that you could do in terms of Googling, working on Stack Overflow. Make some progress on your working prototype. Have something minimal, viable prototype that kind of conveys your idea of what you're trying to build. And then after that, you could take that prototype for having a much larger conversation. How things evolve from there is you can develop some collaborations with research groups for professors and try to see how like you have to figure out the way to yeah, I think it's also a matter of solving these dead ends with, in terms of looking more ways of solving the same problem, because dead end is giving you some insight on what is not going to work. And yeah, I think these three things, that make sure, if it is implementation issues, go to Stack Overflow. If it is something you want to progress further after a working prototype, go to research professors network and try to find some collaborations. And third, if it is a dead end, a complete dead end, try to think of other possible ways of doing it, like have an open mind about it. Okay, there's this question about, for explainability, did you compare data generated explanations with human explanations? Like maybe documenting what a person they are thinking and checking if the data generated explanations of it could be matching that. That's a very interesting question, and it's actually a very, very active area of research. That means the reason I can explain the reason why this is difficult, because think about explanations, they need to cater to your audience. And the method that I was describing, the SHAP method, is a model agnostic method. It's a very computational aspect of having some notion of explanation. Of course, that is not complete. People are looking into how you could sense what the audience is capable of understanding, and then provide that sort of an explanation which helps them understand. An easy way to think about this is maybe a teacher for a first grade student would explain the same concept very differently than they would do to a fifth grade student. So the ability of the audience to grasp changes the way that you explain things. So I would say the sharp value based explanations do not require any, they are not gonna align with human explanations to a great extent. Although the SHAP paper talks about that they did some experiments that showed there is some alignment to the human generated explanations. But for these sequential tasks, humans bring in a lot of prior knowledge, which has to be modeled in the way that these feature space we represent for the machine learning model. Okay, next question. Don't you think deep learning has started hitting its limitations? I think that it's not true. There's a lot to be done in deep learning. I think one important aspect that's missing is this is a purely statistical approach with which needs to be made more efficient with prior knowledge. So a very inspiring story is Maybe people know about multi-layer perceptron. Essentially, it is just a weight matrix that you want to compute on how to process your data so that it spits out the required labels. So you learn those weights. So that's pretty much the concept of a multi-layer perceptron. Incorporating prior into this is actually something which brought the success of convolution networks. So convolutions are something which take the prior about the um, the spatial structure that we see in images and the fact that those patterns repeat over and over in several images. So there's no need to learn a huge weight matrix. It brings down the computation to much lower levels and enables the neural network to actually learn something. So convolution is something where this structural prior helped a lot, and that intuition came from images and signal processing to a large extent. And the deep learning community, machine learning community in general, this needs a lot of these prior knowledge or structural concepts to actually make things more efficient. Apart from that, I think statistical techniques have shown a lot of promise, especially in reinforcement learning. But sadly, we see them working all in simulation. So how can we bring those solutions that look very nice in simulation to the real setting? And that is also a good avenue for research. So I do think that there's a lot of potential to identify interesting problems in deep learning and machine learning research still. Okay. Moving on to the next question. I think the ordering got somehow shuffled. So, is this problem similar to the problem that postal services face while delivering packages, reaching every point in a prioritized order while minimizing time? Okay, so so is this relating to the second problem about learning spatial semantic priors? Um, I'm guessing that it's talking about the same problem. No, actually, what postal services do is a traveling salesman problem. They very well know the scape of the land and they know how much distance it is going to take to one city to another, one delivery house to another, and they are trying to optimize the path which would take to cover all the nodes in the graph. This problem that I was talking about as a second project of mine was slightly different. It was about that how can we incorporate the knowledge of typical household objects and their spatial co-locatedness with other objects. Can we use that knowledge to search in an unseen house? Just like you go to your friend's friend house and you're trying to find something such as an apple, you're most likely going to go and search in a refrigerator because you have learned that apples are generally placed in a refrigerator. And there are similar notions like, okay, when you're finding a key for your friend's place, where are you gonna look for it? So the key idea here is the difference between the two problems is in traveling salesman problem, you are assuming that you know the whole graph, the whole the number of nodes and the number of edges between the nodes and their distances. In this problem, we do not know that. We are using our prior knowledge about things we have seen in our training examples, and using that we are trying to find that object in an unseen but similarly structured house environment. Okay. So next question. There is another question. Do you work only on the computational models or do you also work on sensory input? For instance, in cart balancing example, actually obtaining the accurate velocity and angular velocity might be very hard. That's true. That's something, again, the problems of simulation world, that's something I just use because Carpool is typically a very toy environment for people to use for starting experiments in deep reinforcement learning. So when I was trying to generalize that idea that SHAP values can be used for explainability in deep reinforcement learning policies, the first thing I would try it out as a prototype would be the Carpool environment. So this is an environment provided um, and used mostly in all the papers that you would see as a first toy experiment. And since you are in the simulation environment, you basically know these state parameters. So it's a very conventional, classical environment which has these 4 state attributes. But I have mostly worked on, I think, in the computational algorithmic side. And I want to move towards these sensory inputs, how you could actually measure these things in the real setting and then use them for those algorithms. And that's an interesting space, but definitely my focus currently is more towards the algorithmic side as of now. What do you think would have been hyped? Oh, okay. What do you think would have been the hype technique and algorithm had the AlexNet paper not been developed or recognized? That's an interesting question. I don't know. I think that paper kind of shaped the whole way in which we think about reinforcement learning. Prior to that, there were a lot of other techniques like restricted Boltzmann machine, especially for computer vision community. There were more of these engineering-based techniques like SIFT, which was scale invariant, I think, feature transformation. So those were the techniques which people were developing. Before deep learning, I think people focused a lot on symbolic AI. And even now, people are trying to come up with neuro-symbolic representation or reasoning, because people are starting to think about that not everything has to be learned or can be learned in sample efficient way. And is there some way to bake in this knowledge and use the benefits of neural networks at the same time? So what are the prerequisites? Okay, will you be branching into cognitive neuroscience for robotics? Cognitive neuroscience. That is an interesting domain. Maybe not for me. I think because I do work with cognitive science people and psychologists, which do provide some perspective, but not yet with neuroscientists. So that's definitely very interesting area to look into. Okay. What are the prerequisites to start as a research assistant in machine and deep learning? Okay, I think to start in this field, you can maybe study your math courses very well during your undergrad, starting something like linear algebra and basically covering your matrices and calculus very well. It's very important for this subject. And then it depends on the way you want to go. If you want to go into the research theory aspects, having a good grasp over math fundamentals is important. If you want to start off with more of an empirical person, starting out with experiments, getting comfortable with coding in mostly Python, frameworks such as PyTorch and TensorFlow provides a great deal of tutorials on how to get started. And then I think these are pretty much the prerequisites, and then you start reading about something, like pick anything, and then start reading about it, and then assess how much you can understand it, and think about what are the potential research questions that can come up in it. And or another way that you could maybe start this with the top-down approach, just try to Google some interesting, influential researchers in the field and see what papers they have written, what topics they are most excited about recently, if you are really curious to work with them. And that helps because that is important to build a connection with the potential advisor, so that as a research assistant, they're happy to advise you or help you in your research project. So I think it's both ways. Like, you can start bottom up or top down. This is an interesting question that people should think about more. Okay. Wanted to know about your decision to pursue an MS instead of PhD, while the former is usually preferred for research roles. I do actually want to pursue PhD, but MS is something that I had as an option at that time. And the good thing about the MS program here at CMU is it's a research master's program. So at the end of it, I am going to write a thesis, and I will be moving towards something which is more research focused rather than course-based masters, which typically asks you to do a lot of courses and then you are more set for taking up a job. So this program itself it's a very unique space to understand whether research is something for me or not. And this is I think okay, because at times you want to test whether with a small amount of duration, that whether I'm able to do this research or not. And PhD seems like a very long-term commitment for 4-5 years. So doing a research-based master's is a good way to understand your research outlook, like how do you want to do. For me, I think I am interested in both in research positions as a PhD student as well as in the industry, and I'm still going to figure out in the coming months where I'm going to go. Okay, so next question is, what evaluation metrics are used while training models to predict human strategies? Okay, so here the evaluation metric was very simple, like how much was the accuracy of these models in saying whether a critical victim was triaged or not, or whether, and in the next room prediction case, it was more like a multi-way classification across all the area segments that were there. So we were evaluating based on how accurate we predicted, where did we predict, how many correct instances we predicted out of the total. So yeah, we did not go into a lot of evaluation metrics because it was just a very exploratory project in a workshop. But it's interesting to think about more evaluation metrics here, such as what are the instances when we predict something incorrectly, and what would be its impact, its broader impact of saying something was incorrectly predicted at this point versus a more critical point. So that problem statement could be evolved even further. Okay. Is it easy to extrapolate RL models trained on simple environments like OpenAI gyms to more complex environments later on? I don't think so. It's not easy, and thinking about an appropriate curriculum about these problems is an active area of research. Like, how would you design a curriculum so that when you train on this, that knowledge of the RL models is actually transferable to the newer, more complex environments? And that comes with the sample efficiency aspect of things. Okay, is there okay, I think there are no more questions. And I think we are out of time now.
Thank you, ma'am, for taking time out of your busy schedule to be here with us today. The talk. Now we'll have a short video of 30 seconds. After that, we'll be moving on to the lounge where if the students can interact with you one-on-one for yeah, like